Okay, so we're continuing to march through our nice table of discrete random variables. And this lesson, we're going to focus on the hypergeometric random variable, which is another one that's easiest to make sense of if you contrast it to the binomial random variable. So let's just zoom in on those two. So like the binomial, the hypergeometric random variable is the number of successes in n trials. But you notice I left out the word independent there, okay? The idea with the hypergeometric random variable is we are specifically thinking about sampling, about drawing individuals, a sample, a set of individuals from a broader population. And there is a kind of a Bernoulli trial aspect in there that each item that we draw is a success or a failure, whatever trait that's going to be, red or blue marble, voter, non-voter, however you want to think about it. But the trials are not independent for the hypergeometric distribution. The hypergeometric distribution kind of goes with the slogan, sampling without replacement. Okay, so if we've got a broad population, we're choosing all of our sample at once, which means you can't draw the same person, the same marble, whatever it is, twice. Okay, that means we're going to see that the trials, the choices, the draws, so to speak, are not independent of each other. Okay, so and that's in contrast to the binomial distribution, which one way we could think of the binomial is we can map it into this sampling framework, and it would correspond to sampling with replacement. Okay, so just to start thinking about this concretely, let's actually start with the binomial. And let's say we have a population of 10 people and 8 of them are voters and 2 are non-voters. Okay, so just drawing that out here. We've got 1, 2, 3, 4, 5, 6, 7, 8 yeses for voters and 2 no's that are non-voters. And we're drawing people from this distribution one at a time. And for each time we draw somebody from this, each time we pick somebody from the 10, the probability that that person is a voter is 0.8. Okay, the trials are independent because whoever we drew, we just put back in and it's start all over again. So in that sense, they're independent, and the probability of being a yes is always the same, no matter what it was before. Okay, so that's, again, that is sampling with replacement. And that is indeed the kind of image that we have in mind when we use the binomial random variable. Independent draws, same probability of success in every trial. Okay, so now let's think about the hypergeometric random variable. And the same population here. Okay, so again, we're going to start off with 8 yes people, they are voters, and the 2 no people, they are non-voters. And here, for the first draw, just like the binomial, the probability that we get a yes for the first draw is 0.8. Okay, but now we're not replacing that person. So for the second draw, if we do indeed have a yes on the first, then for the second draw, there's only 7 yeses left. Okay. And there's the 2 no's. So the probability that we get a yes on the second draw, conditional on getting a yes on the first, is only going to be 7 out of 9. Okay. And what if we got a no on the first. Okay, then we'd have all 8 of our yeses would still be in there. We have only one no, and the probability of getting a yes on the second draw, given that we got a no on the first, is 8/9. Okay, so that's the deal with how replacement affects the probabilities here. Again, you want to notice that the probability of getting a yes on the second draw is different than getting a yes on the second draw conditional on there being a yes on the first is different from getting a yes on the second conditional on there being a no on the first. Okay, so this shows us that the draws are not independent. It's also true that the probabilities are not constant across the trials. Usually when I think about sampling without replacement, hypergeometric, I don't think about like taking them out one at a time. I think about reaching my hand and grabbing them all at once. I think that's a metaphor that or visualization that most people use. Okay, so that's the difference. And it does mean that the probabilities, the probability mass function is different for the hypergeometric random variable. So let's look at that. Let's go to another screen here, and it's going to be more complicated. Okay, the binomial is a cleaner, more general, easier to work with distribution than the hypergeometric, because the hypergeometric actually depends on the size of the sample, the size of the population. It's got more parameters to it to actually calculate those probabilities. And that should kind of, make sense to you. Whenever we let go of independence assumptions, we have to start thinking about conditional probabilities and things get more complicated. That's not as true in the hypergeometric cases it could be, but it's a little bit true. And we do have a few more parameters. So the way I'm going to parameterize the hypergeometric distribution is I'm going to let capital N be the size of the population. Okay, so the number of individuals in the population. And I'm going to let small n be the number of individuals in the sample. Okay, so we've got this broad population of size big N, and we're reaching in and we're grabbing out small n people all at once. Since we're doing it all at once, there's none of this with replacement. Okay, you can't be in the sample twice this way. And the other thing that we need here is M is the number of successes, whatever that is, red marble, voter, however you want to think about it, in the population. Okay, so those are the 3 parameters. 2 things that we can calculate from that that are sort of helpful to think about are, one, we can think about the fraction of successes in the population. Well, that's just M, the number of successes in the population divided by the size of the population. There's nothing tricky here, but that's a useful thing to think about because that's kind of the analog to the P in the binomial distribution. Okay, so the proportion of successes in the population. And the other thing that's just, we might want to think about what it looks like is N minus M is the number of failures in the population. Okay. So with these parameters that imply these other quantities here, we can write down the probability that in a sample of size small n, the number of successes is I. Okay. So remember, it's still the same question as for a binomial. We're asking how many successes do we expect that's our I, in a sample of size little n. And here's what it is. It's m, choose I, times capital N minus m, small n minus I. Okay, so m choose I, big N minus m, choose small n minus I. That's kind of a mouthful. And down here in the denominator is capital N, choose small n, big N, choose little n here. Okay, that looks unfriendly, but let's just think about what we've got here. Down here in the denominator, what we have are the number of samples of size little n possible in a population of size big N. That is like literally what big N choose small n is. How many different ways are there to select small n things from a broader group of big N? Okay, so it's the number of total samples. Then what do we have upstairs here? Okay, well, we have this m choose I part here, and that is the number of ways to choose I successes in the sample from M in the population. Okay, so like just imagine that urn and it's got red marbles, those are successes. And what we want to know is what's the probability that I get I of those successes in my sample? Well, it's the number of ways that I can get the I successes that I need from the broader set of M. There's M of them in the urn. There's other stuff in the urn too, but how many different ways are there for me to pick the I successes that will show up in my sample? Okay, which is what we're asking about here. And this part here is the number of ways to choose the capital N minus M failures in the sample from the, oh, wait a second, I got that backwards. The N minus M are not in the sample, they're in the population. It's the number of ways to choose the small n minus I failures in the sample. Okay, that's how many, if we're looking for the probability that we have I successes in the sample, we're going to have N minus I failures in the sample. So how many different failure groups from the population can we choose? How many different failure groups of size N minus I given N minus M? That's capital N minus M, choose small n minus I from the, finish my thought here, N minus M failures, sorry to switch colors here, in the population. Okay. So the way to think about the components of the numerator is in the sample, there's M successes. How many different ways can I draw I of them? And there's N minus M failures. How many different ways in the population, how many different ways can I draw the small n minus I failures? And what the total, the numerator, both terms together, tells us the numerator overall is the number of possible samples with I successes and N minus I failures. And that's what we want, right? Okay. We're looking at for the probability that I have I successes in my sample of small n, and of course that means that I have n minus I failures. Has to be that way since all we have are successes and failures. And so to get that, it's just the number of possible samples of small n I can draw from a population of big N divided by the number of samples that satisfy my criteria, which is that there are I successes and n minus I failures. Okay, so that is the PMF. Those are the probabilities. Something I want to kind of emphasize here is that in contrast to what I was doing over here on this board when I was talking about the probability of what would happen on the second draw, that's really not what the hypergeometric random variable is about. So maybe let me amend what I've got here to say that this is the hypergeometric scenario here, okay? What the random variable is looking for is the number of total successes. We don't care whether it's happens in the first draw or the second draw. And indeed, usually when people think about the hypergeometric, they're thinking about drawing the whole sample at once. And that idea of drawing the whole sample at once, reaching in your hand and grabbing a handful of marbles that will have some reds and some blues, that to me is the easier way to parse the probability. Okay, so I've got a few more things to say about the moments of the hypergeometric random variable, but I'll do them in their own little lesson.